Hello, I'm the mostly harmless Mr. Daycock, and today I'm going to be teaching you about how differentiation relates to the instantaneous gradient of a curve. Okay, so for example, here we have a curve y equals x cubed. So that is the curve y equals x cubed. Now, differentiation, we were talking about it in terms of velocity. We said that velocity was equal to the change in our position x over our change in time t. And then what we did was we let that change go to 0. The change was described as h in our formula. H goes to 0 and we would get dx by dt. But we said, you could call it dy by dx if you wanted. But what does dy by dx mean? Or the change in y by the change in x over the change in x mean? Well, that's the gradient of any line. If you've got a straight line, the gradient of it is the change in y, i.e. the distance of the y, divided by the change in x. This is the gradient of the line. So this here can be considered the instantaneous gradient, the gradient as things that change goes to 0. So here's how it works on a graph. If I were to take a point at 2 and then the point at 3, so because this is y equals x cubed, that's 8 and 27. So I put in 2, I get 8, and here I get 27. So clear. This is the point 2, 8. And up here we have the point 3, 27. And if I were to connect those 2 points by a straight line, well, what do we get? The gradient of the line is going to be equal to the change in y, which is 27 minus 8, over the change in x, which is 3 minus 2. And that's going to give us 19 over 1, which is 19. And so the gradient of the line connecting these 2 points together is 19. But if you notice, that's very, very similar to the gradient of this tangent at the point 2. Very, very similar to that tangent. Not quite the same, but pretty similar. So how do we get it closer? Well, we just bring the point closer. If I were to take this point here and a point halfway in between, the tangents are closer. And then if I were to take a point here and a point, those 2 points, the gradient between the 2 points is much, 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 much closer to the gradient of the tangent. And so if we let that limit tend to 0, that difference between on the x tend to 0, what that means is our gradient of the tangent is equal to our dy by dx. And this is why in the last video I was talking a lot about using dy by dx rather than dx by dt, because a lot of the time in mathematics we talk about differentiation as finding us the gradient of a curve at a particular point, or the gradient of the tangent. So in this case, the gradient of the tangent, well, this is the curve y equals x cubed. By our power rule from last video, that means dy by dx is going to be equal to 3x squared. And if I plug in the x, and we know that at the point 2, 8, our x value is equal to 2. If I plug that in, I get dy by dx is equal to 3 times by 4, which is 12. And obviously not exactly the same as 19, but actually not too far off 19 in terms of gradients. Although 19 is a much larger number, in terms of angle of a gradient, it doesn't make a huge difference, the difference between 19 and 12. Okay, so here's some examples. Find the equation of the tangent to the curve y equals x to the power of 4 minus 5x plus 6 at the point 0, 6. So we want to find dy by dx first, dy by dx, and we can just use our power rule. X to the 4 differentiates to 4x cubed, and again we're going to differentiate each term. So x to the 4 differentiates to 4x cubed. minus x to the x5 differentiates to just minus 5. And the 6 will differentiate to 0, so we can just ignore it. So we get 4x cubed minus 5, and this here is our formula for the gradient. And so the gradient at x equals 0, because we're looking at x equals 0, so the gradient at x equals 0 is going to be dy by dx evaluated at x equals 0, and this is often how you write evaluated at a particular point, is going to be equal to 4 times by 0 cubed minus 5, which is equal to minus 5. And so the gradient at x equals 0 is minus 5. But the question asks for the equation of the tangent. Now, an equation of a tangent is a straight line, and the equation of any straight line is going to be of the form y equals mx plus c, where the m is the gradient and the c is the y-intercept. So we're looking for something of the form y equals mx plus c, but we already know the m. So in this case, m is equal to negative 5. So we're looking at an equation of the form y equals negative 5x plus some c, which we don't know yet. C is our y-intercept. So now we have to ask ourselves, well, do we know any point that this line goes through? And the answer is yes. Because it's a tangent at the point 0, 6, that means it must also go through 0, 6, because that's the definition of a tangent, that it meets that curve at exactly that point, the point in question. So we're taking this line y equals minus 5x plus c, and we want to plug in that 0, 6 to find the c. So we're going to get 6 is equal to minus 5 times 0, because remember our x here is 0 and our y here is 6. So I'll just plug those in, plus c, and that gives us, simplifying that, we get 6 equals c, which means that c equals 6. And then we have our final answer of y equals minus 5x, which was from our gradient. This was from the dy by dx, plus the 6, which is from putting in the point. And we do each of these things because they find us what we want. There's not so necessarily an inherent procedure that's required, but it finds us what we want. And what's quite nice in this case, because the question asked us for the gradient, for the tangent at when it crossed the y-axis, it meant our y-intercept was actually fairly easy to find. But in this example, it's going to be a little bit less easy to find. So we're going to do the same thing again. We want a line of the form y equals mx plus c, where m is our gradient and c is our y-intercept, and we need to find those things. So for the gradient, we want dy by dx, and that's going to be equal to 5x to the power of 4 by the power rule, plus 4x, again by the power rule, plus 0, again by the power rule. And then we want to evaluate that at the point we care about, which is 1, negative 3. So we want dy by dx evaluated at x equals negative 3. And that's going to give us, oh sorry, not x equals negative 3, let's be careful here. The y is negative 3, but the x is equal to 1. So evaluated at x equals 1, and that's going to be equal to 5 lots of 1 to the power of 4 plus 4 lots of 1 which is equal to 5 plus 4, which equals 9. And so our line, we know, is going to be y equals 9x plus c. Terribly drawn 9. Let's do that again. There we go, much clearer. 9x plus c. And now we want to find out what that c value is. So we plug in the point. One, -3, because it's a tangent, and because it's a tangent, it has to go through the shared point, 1, -3. And we're going to get -3 is equal to 9 lots of 1 plus c, which gives us -3 is equal to 9 plus c, and then we need to subtract that 9, which gives us c is equal to -12, just by solving equations in whatever way you like to solve equations. And then that gives us our answer. Y is equal to 9x minus 12. And we're done. That's the equation of the tangent to this curve at that point. And if you want to think about what it looks like, it's going to look something along the lines of a nice power of 5. We've got quadratic. It's going to go through here. It's going to look something like that. And we've got this point here is our tangent. Let me draw that better. And we're going to get a tangent sort of at this point here, 1, -3, and it's going to cut through like this. So that there is our point -12. This here is the point 1, 3, and our gradient is 9. So this is the line we found out the equation to. And this here is our curve, x to the 5 plus 2x squared minus 6. And this is the line y equals 9x minus 12. And as you can see, they are a tangent just at that single point. Interestingly, it will actually meet again further down here, so it's not always necessarily true that tangents never meet again, but they won't meet with the same gradient. They'll just cut through each other because they're two lines that do.